For this chapter of notes on electrical systems, I'm providing three examples. Examples 1 and 2 look the same, and I originally had some different ideas on what I would do on examples 1 and 2. But what I've decided to do here is only do example 1 and modify it a bit. Example 1 is just going to be a straightforward application of Kirchhoff's current and voltage laws combined together. And what we want to come up with is for an input voltage there of VI, what we want to do is come up with a differential equation which describes the output current that goes through the inductor right here. That's our goal. So the steps we're going to go through are listed here, and we'll go through them one by one as we get to that point. C, I'm going to change this to Kirchhoff's current law and voltage law. We'll use them both, ending up with our differential equation. All the rest of it stays the same. Also, when we get through, we want to find the Laplace domain transfer function. Again, for the output of I2 with an input of VI. Well, the first things that we need to do is define our sign conventions in terms of current and voltages. The currents I've already drawn those in. I've somewhat arbitrarily drew I1 and I2, I3, and I2 here is the same here. I'm going to label some nodes here. So I'm going to call this node 1, this node 2, B over here is going to be also called node 3, down here on the bottom is node 4. So the voltages at all these nodes at the bottom are the same, so they're all named 4. But an important thing in order to get the right sign conventions for our elemental laws is that we recall that current flows from positive to negative in our passive elements here. So this is a plus and a minus in terms of voltage. Again, plus and a minus. All these are done because of the direction of current flow through these resistors, inductors, and capacitors from positive to a negative. Those come into play when we write down our elemental laws. So in fact, let's do that now. So the first step is going to be write down our elemental laws for the resistors, capacitors, and inductors. So for resistor R1, we'll say V1 minus V2. That's equal to the resistance R1 times the current I1. Again, we're looking at the sign conventions that we have here on voltage and the direction drawn for I1. And with that choice, there is a plus sign there in front. So this will be equation 1. If we look at resistor 2, it's the same thing. The voltage change across resistance 2 is going to be V2 minus V4, and that's equal to R2 I3. The inductor, the voltage change across from 2 to 3, V2 minus V3, we know is equal to the inductance times the time derivative of the current flowing through that inductor, so that's di2 dt. The capacitor, what we have here is the capacitance times the time derivative of the voltage across that capacitor, and our sign conventions here say V3 minus V4. We know that that's equal to the current flowing through the capacitor, that's I2. And then for our source says that if we go V4 minus V1, that's going to be minus VIT, our input voltage there being VI. So I'll fill out the naming here. This is equation 2, 3, 4, and 5. Very important to name your equations because it helps you keep straight in your mind what equations you're dealing with, and then if someone such as myself has to grade your work, it's a lot easier to follow what you are doing. So let's write down the current law first, the current node law. And I'm going to apply that for node 2. I'm going to scroll back up so we can see node 2. In node 2, we look at I1 flows in and out flows I2 and I3. So this node law then is equation 6. Next, we're going to write down voltage loop laws. We have 2 of them because we have 2 loops in our circuit. So let's say we look at loop 1, and loop 1 is going to be this one here. And later on we'll do the same thing for loop 2. So for loop 1, we go through, we write down V1 minus V2. We start there at node 1. That's the voltage across the resistor. And then we have V2 minus V4. That's across the second resistor R2. And V4 minus V1. We check to make sure that we have our signs right in all this, and we see our check here works in the sense that this V1 will cancel with that, V2 cancels there, V4 like that. So for sure that works out in terms of signs. So what we'll do now is we'll take our elemental laws 1 and 2. Elemental's law 1 and 2 says that V1 minus V2 we saw was R1 I1. V2 minus V4 was equal to R2 I3. And V4 minus V1, that's minus our input voltage VI. Then from this equation I'm going to enforce elemental law, our current node law of 6. So that's I1 is equal to I2 plus I3. And I group together terms, I get R1 I2 plus R1 plus R2 I3 minus VI. So from this one equation then, we get that the current I3, we can solve for that in terms of I2. We don't really want to find I3, so we can eliminate that. So it's VI divided by R1 plus R2 minus the ratio of R1 to R1 plus R2 times I2. So this is equation, which I'll refer to as equation 7. If you go back and look at the figure for the circuit above, we do the same thing there for loop 2. I start at node 2 and say V2 minus V3, V3 minus V4, plus V4 minus V2. And again, we check to make sure that we have our signs right. And the signs check out because that cancels with that with that, and V4 with that. So that really does work out. But what we want is not so much that it's a 0, but we want to put in our elemental laws here. Looks like equations, elemental laws, equations 2 and 3. Equations 2 and 3 substituted in there gives us an L di2 dt for the first voltage drop. We'll keep V3 minus V4 as it is just for the time being. And then V4 minus V2, that's minus R2 I2. We take a time derivative of this. And the reason we're taking a time derivative, and the reason I didn't put anything in here for V3 minus V4, is we see V3 minus V4, we need a time derivative of that. Okay, so if you take a time derivative of that equation there, we get L times the second derivative of I2 dt plus the time derivative of V3 minus V4, that ends up being an I2 divided by C minus R2 di2 dt as that. And then, I'm sorry, I think I've got some mistakes here. This should be an I3, V4 minus V2. What was that? That's right, that was a subscript there of 3. So please make the subscript change here. There should be a subscript of 3. di d3, that's coming in from equation 7. So if I now substitute in intermediate equations 7, I get L, second derivative of I2 with respect to time, plus I2 divided by the capacitance there of C, minus R2 di3 dt. That's the time derivative of our input, divided by R1 plus R2. It's coming from equations 7 above, minus R1 divided by R1 plus R2 times the time derivative of I2. And I simplify this out. I group together terms, and I'm going to multiply through by C and get LC times the second time derivative of I2 plus I2 plus R1, R2 times C. Again, I multiplied through by C to get rid of the C in the denominator of that one term. R1 plus R2 all times the second derivative of I2, I'm sorry, times the first derivative of I2 with respect to time. And the right hand side, I'm going to have, when I bring my input voltage on that side and I multiply by my C, I get R2C divided by R1 plus R2 VI dot. So that's the thing we're looking for. We're looking for our single input-output equation, output being I2, input being V sub I. So in terms of our transfer function, since we're looking for forced response, we take Laplace transform with 0 initial conditions, and we get LC times S squared, all times the Laplace transform of I2. I have an R1 R2 times C divided by R1 plus R2. That's multiplied by a Laplace variable there of s. We have an I2, which is going to appear as a 1 here. Laplace transform of our input I2, that's of s. And right hand side, that's R2C divided by R1 plus R2 times S times the Laplace transform of our input VI. So here we are. I2 output is equal to R, I'm not quite sure where the RC came from, that should be an R2. Be an R2C divided by R1 plus R2. In the denominator, I have an LC squared plus R1 R2 divided by R1 plus R2 times C times S plus 1 all times SVI of S. So there's a factor of S in the numerator. This is a transfer function. This is the transfer function between the input VI and the output of current I2. So the process we went through was a tedious one, I think. We had to be on our toes right from the beginning, particularly in sign convention. So it's very important that you label your currents. I usually label those first, then go back and put my plus minuses on the voltages, because that gives us the correct signs on elemental equations for R1, R2, L, and C, as well as for our input. We apply the Kirchhoff's current node law, Kirchhoff's voltage law, and from there it was a matter of algebra, differentiation, and getting it all down into that form. Again, the voltage loop laws, there were two of them, but again, at that point, it was a matter of being patient and being very precise in terms of signs and things as that. And that's our equation we're looking for. That's our transfer function, G. In the next example, in example 3, we'll see a better way where we actually, somewhat like we did for mechanical systems, we deal with the Laplace transform of our elemental and voltage laws and things like that, in addition to this idea of a complex impedance. And we find out that that process, which is algebra rather than differentiation, is a lot more straightforward than this and less tedious.